Well, good morning, everybody. My name is Paulo Arguelles. To my right is Dennis Viveros, Kevin Chaput, Steve Keenan, Joshua Vasquez, and Dong-Lei Lee. We are the CubeSat design team, and this is our system requirements review presentation. So here's a little bit of what we're going to talk about today. First, we're going to go over the significance behind our project. Second, we're going to go over our project programmatics. Third, the bulk of the presentation will be focused on design overview and also design trades. And lastly, we're going to give you a summary and give you an argument as to why you should care about our project. But before we get into any technical minutia, I want to introduce you to something. Okay? Folks, this is the future of space exploration. It may not look like much, but trust me, this little guy packs a lot of punch. This is the outer chassis for a small satellite, 10 centimeters on each edge. We call it a CubeSat. You know, it's one thing to just tell you these specs, but it's another to see this thing in person. I mean, it is marvelously small. Pack this thing with electronics and space subsystems, and the possibilities are endless. Who knew that a spacefaring satellite could fit in your backpack? Pretty amazing. CubeSats such as these are defined in terms of units. So this is a 1U CubeSat, 10 centimeters on each edge, with a mass of 1.3 kilograms. In fact, you can stack these up to be as many as 12 U's in volume if you wanted to, depending on your application. But let me tell you a bit about what we propose to do. We want to prototype a 3U CubeSat, and just to give you a sense of how unprecedentedly small this is compared to NASA's normal spacecraft, here's a size comparison with NASA's Juno. We like to think of it in terms of a soup can, a loaf of bread, and a tour bus. It really shows you the relative size of these things. Thanks, Kevin. Many of the satellites currently exploring our solar system today fall between 500 kilograms and 10,000 kilograms. But when we say small satellites, what we're really thinking about are satellites that are below 500 kilograms. CubeSats fall into this category. Within the small sat category, there are picosatellites, nanosatellites, and microsatellites. So when we say CubeSats, we're really thinking about picosatellites and nanosatellites. So, Cal Poly has a CubeSat. CSUN has a CubeSat. Well, those of us here at Cal State LA, we want to be the next ones up there. And so in addition to prototyping the basic spacecraft subsystems, we're also going to need to elevate the TRL of some new emergent technology or capability. And that's how we're going to get that NASA funding. And we think we found the perfect technology for this. Clearly, solar sailing is the way of the future. It's a passive form of propulsion using a giant reflective screen and the propulsive radiative power of the sun. Pictured here is LightSail A, which is the Planetary Society's successful attempt at deploying a solar sail in low Earth orbit using a 3U CubeSat. And if you're still not convinced as to the potential and power of this technology, get this. Using conventional thrusters, it would take us 2,000 years to reach Alpha Centauri, our closest star system. But using solar sails, we can make the trip in 20. So this thing is book-in. It can go as fast as 20% the speed of light. And all this really informs our project scope. It can best be represented in two parts. The first part deals with our bus, the CubeSat system, where we're going to have to demonstrate competency in the 8 listed spacecraft subsystems here. And the second part deals with our experimental payload, namely our solar sail, where we're going to need to develop a deployment mechanism so that we can hopefully use that to demonstrate some rudimentary pointing capability for the solar sail. And with that, I'd like to toss it over to Dong-Lei, who will talk to us about programmatics. Dong-Lei.
Thank you, Paulo. Hello, my name is Dong-Lei Lee. Now, we have our mission established. This is time to plan and take actions. Now, I'm going to talk about deliverable, program organization, and schedule. Next slide, please. As you can see, we have 6 items that we're going to deliver throughout the year. 25 agenda and minutes that due weekly, 1 system requirement review that we submit in this week, 1 preliminary design review that in December, and we have 3 items gonna do in 2008 in May. They are final design review, final report, and prototype. These are the key that will lead the functional CubeSat prototype, and we're looking forward to doing it. Next slide, please. mission cannot live without exceptional team cooperation, dedication, and commitment. This is how our organization is going to do. We divide it into 3 groups: administration, CubeSat, bus, and solar payload, and solar cell as our payload. We have Dennis, Steven, and Yusua gonna take care of solar cell as a payload. We also have Dennis, Paulo, Kevin, and I working on solar cell bus. If you have any question, we're going to consult with our current lead, Yusua. Also, our industry liaison, Carl Salinas, faculty advisor, Dr. Neely, and our instructor, Ted Knight. Also, if you need to purchase parts for our design, we will contact Evan Lee. Next slide, please. As you can see, we are on schedule so far, and we are ready for the next phase. I will turn to Yusua.
I'll be going over our system requirements. But before we do this, I'd like to highlight what contributes to our final list of system requirements. If you go to the next slide, please. These aren't in any particular order. At the top, we have NASA INSPIRE, which is a way in which we are able to solicit research opportunities through NASA. Second, we have Technology Readiness Level 3, TRL 3. Now, NASA has a way of gauging technology maturity, and that's for TRL 3 is through analytical and experimental proof. Third, we have size, 3U. Because we are secondary payload, we are allocated a certain amount of space, and we have to stay within. If we go to the next slide, we'll go over our system requirements. At the top, our team of electrical engineers have come up with some numbers as far as power consumption and bus voltage. Power consumption at less than 8 watts, and bus voltage at 12 volts. Because again, we are secondary payload, altitude is something we really want to be able to be able to do. If the next space shuttle is going 250 kilometers of altitude, we want to be on it. If it's going 2,000, we want to be on that too. So that's why it's that range. As far as temperature, we're also looking at negative 20 degrees Celsius to 50 degrees Celsius. And as far as mass, this is a 3U, so it's 1.3 kilograms for each. So we're looking at 3.9 kilograms for the whole 3U. And dimensions, this is a 10 by 10 by 30. And on the next slide, we'll go over a little bit the suggested orbit profiles. One of the ones we're really looking at, but really concerned about too, is LEO, which is really, it's least expensive, but we do have to worry about atmospheric drag. So that's one of the things we're focusing on. There's also the sun synchronous and the geosynchronous. And at this time, I'd like to go ahead and hand it to Steve, who will go over our next slide.
Thank you very much, Joseph. So with those requirements in mind, we will now go over the overall design of the 3U CubeSat standard CubeSat with the attributes of solar sail in mind. Next slide. So this is a subsystem tree which lists our subsystems and how more or less they interface, generally speaking, leading down to our payload, which is the solar sail, the attitude control. Starting with our command and data handling subsystem, composed of onboard computers or microcontrollers. Beauty of these components off the shelf is that they are open source, readily available, and TRL9, space-proven components that you can actually Google some of the code to operate these systems. We're also looking at rad-hard hardware. As the mission matures, in the event that we want to go to higher altitude or higher apogee, we want to be able to protect the spacecraft from high energy particles. So those are a consideration for maybe down the road. But for now, we'll stick with the basic by microcontroller Arduino. Next slide. Okay, so this brings us to the communication system. It's probably one of the most important subsystems. Failure of the system means mission failure. I won't mention any names, UCLA, but we want to stick with probably some basic radio frequency, UHF or VHF, some whip antennas. We're also looking at some other communication subsystems, your state-of-the-art, latest and greatest stuff. Again, with the considerations of mission maturity down the road. But for now, we're just gonna probably rely on the radio frequency. So that brings us to the attitude control system. So we want to look at how we're going to stabilize the spacecraft. As it tips out of launch vehicle and starts to tumble, we're going to want to stabilize it, maybe using reaction wheels or magnetorquers, or maybe both. This is a lot of mass, a lot of wiring. It's not simple either. So we may just end up with a GPS chip with maybe an antenna, relying on our solar sail for some attitude control there, but definitely keeping the reaction wheels in mind. And then bringing us to the shifting over to the power system, power management and distribution, handled by EPS, electronic power control system. And all these components, the solar sails, the solar cell, solar panel, and batteries are all COTS, are all components off the shelf, are all TRL9, readily available. Dennis will walk us through some of the options for avionics there and power management systems. Thermal control system as well. These are components off the shelf that are readily available, space-proven components. There's a number of options there. Kevin will run us through the list on these components and see what some of the most likely options will be for that system. Structures. This is your basic, really basic standard CubeSat layout. Dimensions-wise, and our mass constraint for the flight mass is 1.33 kilograms per U. This is 3U, so it becomes more or less a materials selection challenge. So there's a number of options there that Kevin again will run us through on that. So perhaps probably one of our most important subsystems is our actual payload. This is the solar sail. You can see that this can be analyzed with the formula. This is actually a simple formula compared to the real analysis that can go into it, but it has a number of variables there. It's a function of mass, vehicle mass, sail area, and all of these variables can be basically tabled and analyzed and coming up with an acceleration that might match what acceleration we want at what altitude we want. So we might build a parametric table to begin to come up with some design drivers. Get it down to about 2 or 3 options there, and figure out, will we be able to get some attitude control out of the sail? So that leads us to our last slide of the subsystem. This is actually kind of a conglomerate of a couple subsystems. We have some options, geometric options for the sail that we need to consider that directly affects our attitude control, our structures, our deployables, our propulsion, pretty much all subsystems. And we can look at some origami options and how to fold it and maybe store some strain energy to help it deploy. And basically see what is the best. Is it square or is it round? So with that, I will turn this over to Kevin, who will run us through the details of the mechanical design.
Thank you. I'm Kevin, and I'm going to be going over some of the mechanical details and doing some trade studies. So on the left here, you have a triangular, rollable, and collapsible boom. It's wound around a spool, tightly wound around a spool, and it telescopes out. And on the right, you have a collapsible tube mast, which consists of 2 bell-shaped halves joined together at both ends. And so both of these are flattened around the spool, and as they telescope out, they take either a triangular shape or a lenticular shape. So this is a basic layout of the deployment process. Typical deployment, you have the 4 black cylinders in the middle, which are storage wheels that house the boom. And on the corners, you have the 4 blue cylinders house the sail material, which is wrapped around. And as the boom's deployed, it's attached to the sail on either sides via ropes, and they unfurl together. And on the picture on the right is a different variation of this deployment process, where you have 4 booms on each corners, and with that and they're connected to the sail material. And when those deploy, each one of those has 2 booms that take the sail with it. So essentially, you get 4 independent sails. And so with 4 independent sails, as you can see here on the left, it would allow for better maneuverability and actually really allow it to steer better. And the mechanism on the right side, you can see that to control these booms consist of a series of hinges and connecting rods that are driven by little motors. So of the 3 different kind of solar cell materials that are under consideration, analysis showed that the aluminized mylar would be the best option due to its thickness and reflectivity and emissivity of oleofoam were identical, so that was negligible. And regarding the deployment mechanisms, analysis showed that the track boom would be the best option due to its compact packaging height. And regarding materials, even though titanium is widely considered as a super alloy for its CubeSat, it's not necessary. The 6061 aluminum will do just fine, mostly due to its machinability rating and its cost. So another thing we need to take into consideration are the thermal control mechanisms. Passive thermal control is optimal for CubeSats as they require no electronics at all. The way this particular louvers work are that they are controlled by actuators connected to blades that are temperature sensitive, and when they're exposed to high heat, they open and they release heat, and when it's cooler, they close and they are able to conserve the heat. We're currently analyzing data to determine the best TCS to implement, and if it's determined that the passive mechanisms are insufficient, other options will be considered, such as multi-layer insulation and surface coating. So to sum up, the aluminized mylar is the best option for the steel material due to its thickness factor at 0.9 microns. And the reflectivity is, well, just a little definition. The reflectivity is the amount of solar radiation that it's able to reflect. So 0.9 means that it can reflect when solar radiation hits it, it reflects about 90% of it. And emissivity is the percentage of solar radiation that it absorbs. So 0.63 would be it's absorbing 63%. So you want the side facing the sun to be a reflective material. And as far as the deployment mechanisms go, the track mechanism will be the best option due to its compact packaging profile. And as far as baseline for materials, the 6061 aluminum is going to be the best option due to its low cost and mostly machinability, because in order to save money, we might have to build this in-house, and that machinability will really allow us to manipulate the metal and get it into the correct configuration that we want. So now I will hand it off to
Hello everybody, my name is Dennis Riveros. I'll be presenting some of the electrical system requirements. So in order for us to talk to our CubeSat up in space, we need to have some kind of communication method. That communication method is going to be radio frequency, RF. We need to follow certain guidelines when working with RF, which is why we chose the 437 megahertz range and the 144 megahertz range for our respective downlink and uplink antennas. The reason we have a wide gap between these two frequencies so the antennas don't get confused as to which signal is uplink and which signal is downlink. Another guideline we have to follow is more of a requirement to obtain a quality signal, and that is for us to use frequency shift key modulation. The reason we're using frequency shift key modulation as opposed to amplitude shift key modulation is it's more in line with industry standard and is used more by the big aerospace companies on their space programs. So we follow their precedents to use it on ours. Here we have a very top level block diagram of how we receive and receive the signal. Let's say a stream of bits. We then send it to our frequency shift key modulator, which then sends it to our transmitter, which then sends the output signal down to our ground station. As far as the components that are inside of the blue box, we will conduct a small trade analysis on those components in the next step. Here we have two options. With option one, we buy a frequency shift key modulator from Texas Instruments priced at $12.95 per unit. We then buy a transmitter from SparkFun priced at $3.95 per unit. With option two, we buy one component. We buy one component that's both a frequency shift key modulator and a transmitter. And with option two, not only is it less expensive, which makes sense from a financial perspective, but you can also see that the data rate is much faster, which will help us gather. Here we have two options for attitude control. First, we have reaction wheels. Thanks to Paolo, who was able to self-manufacture some reaction wheel using an old hard drive and a motor driver that he got from Amazon. This worked very well for us. We just need to find a wheel with some more mass. This was also relatively inexpensive, because if we were to buy actual manufactured reaction wheels, they run in the $6,000 range, which is a little pricey for us. So that's what we did this one. Next, we have magnet torquers. With magnet torquers, if we actually buy space-rated magnet torquers, they're also very expensive, and they run in the $10,000 range. We can also self-manufacture these for basically nothing. All we need is 0.18 millimeter wire, copper wire, and a small tube of a cross-sectional area of 6.4 millimeters squared, and we just start coiling the wire around the tube. Both of these options were very well for us, and we should include both of these options in our record. Here we have some power requirements for a few of our components that we're using. As you can see, most of our components use 12 volts input voltage, which given our batteries and solar panels should be no problem. We're also looking at the microcontroller. We're going to use an Arduino because of its simplicity. And I did a small analysis on our Arduino's current requirements and found that it requires 0.33 amps, but that's at a pure maximum if we use all of the pins in that microcontroller, which we will not, so that number will drop significantly. Next, I took a look at some heaters. We're still not sure on which thermal control system we will use, but just in case, I took a look at some power requirements and current requirements of heaters. I found that they're very small, so that would benefit us greatly. Next, I took a look at an attitude control system that's very demanding as far as power requirements and current requirements. This attitude control system had reaction wheels, magnet torquers, a bunch of different sensors. That's where the power requirement of 6.3 watts came from. It's very high. Again, our attitude control system will be so complex, so that number will drop significantly. Given that our battery and solar panels are able to focus those numbers, this should work well for us. And with that, I hand it back over to Paul.
Thank you so much, Dennis. You know, we are really excited to take this project on. And admittedly, we have chosen a pretty ambitious technology. Solar sailing is no easy task. But given that it's really ambitious, it is prudent for us to contextualize our project in terms of where we are now to where we see ourselves going. As a potential third-tier mission, we envision a whole swarm of CubeSats equipped with solar sails, using passive attitude control, maybe for GRSS, remote sensing applications. Earlier in the presentation, we mentioned that the Sun synchronous orbit is a potential orbit contender. And that's great because the Sun will always be in view of the solar sail in that orbit. And that's perfect for polar monitoring applications. And so in order to get to all that, in order to make these eventual applications a reality, it really depends on how well we how well we set the foundation for our project this year. And so our project prognosis is looking pretty good. It's healthy. We are on schedule with everything. We got off to a bit of a slow start simply because out of the thousands of things we could do with CubeSats, we only had to pick one. And that took weeks of research and debate, but we think we're centered on a pretty good one, solar sailing. You know, CubeSats are such a wonderful learning opportunity for students. Second only to commercial CubeSats, there are more CubeSats launched by universities and institutions for higher learning than in any other sector. And that has a pretty powerful message. Gone are the days where space is a domain reserved only for the militaries of the most powerful countries on Earth. Today, anyone with the drive to do so can construct a satellite using COTS, commercial off-the-shelf products. And so in many ways, projects like CubeSat democratize space exploration. And so who knew that thinking inside the box is thinking outside the box? Who knew that thinking small is thinking big? Thank you all very much and look forward to your questions.